Thank you. So there's some irony, I think, in asking me, a former PI of a cancelled instrument on polarization, to do a perspective talk on polarization. And this irony is absolutely not lost on me. But I want actually to thank you for this, because it gave me the opportunity to do something which, as a PI, I could not do, which is to actually take time to read the literature, because the only thing you read when you're a PI are review minutes and technical documentation. And I hope that some of this, the quality of this reading remains in this presentation. And if there is anything wrong in my presentation, it's entirely due to me and not to the authors of the paper I'm going to quote. I can if you want. So as a forward, I will just mention that in principle, we can observe polarization at any wavelength. And I think it was Tuesday that Vianney-Lebouteiller argued for the opportunity to do a UV polarization measurement with LUVOIR, but I'm going to restrict to the far infrared and sub-millimeter, because this is a place where I have some expertise. And it's also a part of the electromagnetic spectrum where the ISM is a dominant source of emission. And as we have just shown, and we've just seen in what I will show as well, we can expect new data in this wavelength regime. And even if there is no dedicated space mission foreseen in the next decade, or even maybe in the decade after, there's hope that we will get far infrared data, thanks to apparently easier to fund CMV studies, as for instance, we've just seen with LIGHTBIRD. And I will confine myself to a rather strict ISM matter, that is a diffuse region. And I think there are a few presentations that will probably focus on more compact regions, star-forming regions in the rest of the day. So this is the outline. I will briefly explain what is polarization, how we measure it, and the challenges. Then I have a first part, assuming that polarization is giving us the magnetic field without any doubts, and then comments about the issues that there are with that, and then go on to the work that we can further do with polarization in years to come. So what is polarization and how do we measure it? So very quickly, we distinguish two kinds of polarization: linear polarization, where we define a polarization angle, which is the angle of the plane of the electric field propagation with respect to the plane of the sky, and circular polarization, where in fact the electric field rotates as it propagates. So for practical purposes in the ISM science, we're mostly talking about linear polarization, and the fact that we observe polarization is linked to the emission process or the propagation medium. And okay, to be able to measure polarization, we need to have an emission source that is coherent. We need to be observing a single population that has a single polarization state with a detector that happens to be that can operate within that coherent time. And that means that in practice, because we are observing astronomical sources where sources actually pile up on the line of sight, we call that most observations are unpolarized. But it's mostly because we cannot distinguish the different polarization states that are on our line of sight. So there was this graph was already shown yesterday. To have polarization, the basic ingredients in the far infrared regime are the fact that the grains are not spherical. In fact, they are irregular, or you can call them, they have a helicity. That means that if you were blowing on them, they will start to rotate. That they are immersed in a radiation field which is anisotropic. And so this radiation field is able to apply torques on the grains, and that there is a magnetic field. And there is now a relatively widely accepted theory mechanism, which is called the radiative torque alignment mechanism, that will first spin the grains and then align this spinning axis with respect to the magnetic field. And that means that you have a population of structures which are roughly aligned with respect to the magnetic field, and this creates polarization in extinction, as any polarizer will do. And it also creates polarization in emission, because thermal emission is intrinsically polarized with respect to the surface of the emitter. But the challenge is that polarization is in fact hard to measure, because in practice, the fraction of polarization are small, if you have a fraction of polarization, which is 20%, 20% of the total power is polarized, that's extremely polarized for an infrared ISM source. You are aided by the fact that the fainter the emission, we observe that the higher the polarization fraction, but still that's a small absolute value. So that means that you need very high signal to noise ratio in total power to be able to measure polarization. And so it can create a sort of frustrating situation where you spend a lot of time acquiring total intensity, but that still gives you a small signal to noise ratio over the polarization. And in practice as well, it implies that the detectors that you're going to use need to have a relatively high dynamical range so that they are able to record both total power and a small fraction of this total power, which is the polarized fraction. And so depending on the technology you're going to use, if you have detectors that are polarization sensitive or not polarization sensitive, this creates operational issues and challenges. So the first part of the talk is going to be what we have learned by this assumption that because polarization is linked to the magnetic field, we can assume that polarization is giving us the magnetic field. And let's work with that assumption first. The importance of this is that, as was said yesterday, and as you probably know, if you compute the number or estimate the energy density, you cannot neglect the amount of energy that is stored in the magnetic field. And since in the ISM, we are trying to understand what is structuring the ISM, what is supporting it against collapse, against star formation, we cannot neglect a component of the energy which is storing about as much as anything else in, for instance, in gravitational energy or in thermal energy. And so there's interest in measuring the magnetic field. The first classical measure when you're attempting to understand the structure of objects is to do morphological comparison. And on the global scale, there's the work that has been done with Planck data, which provided a whole sky map of the polarization and therefore allowed to explore the magnetic field structure with respect to all the nearby clouds of the nearby molecular clouds. And this revealed, for instance, that there's consistency between the magnetic field structure as revealed by polarization and the structure that you see in density. And if you try to characterize it, this small insert is how the relative angle between the magnetic field and the structure in density evolves as a function of the column density. You see that there's a tendency for the magnetic field to be perpendicular to the high density structure, which is interpreted as giving support to this structure against collapse, and to be aligned with low density structure. So it's 0 when the column density is low, and it's 90 when the column density is high, which is then interpreted as allowing matter to flow along this structure, or channeling this matter. We'll see. It will really depend on how much energy is in the magnetic field to understand whether it is following structure formation or allowing structure formation. There has been work done at higher resolution because this was Planck resolution, so there was quite some limitation. And this is a work, for instance, by Arzumanyan et al. On the NGC 6334, where they study how the magnetic field is arranged with respect to the main ridge of this structure and the network of filaments that connect to it. And you can see that globally, the magnetic field is perpendicular to the main ridge crest. And if you look at the network of filaments that is connected to this structure, well, the magnetic field seems to be relatively randomly oriented at large distance from the main ridge, but as the filament converge to the main ridge, they align the field and the filament direction align themselves, which is consistent with this scenario where the magnetic field either favors or traces the flow of matter, the accretion of matter to the main filament, and support the main filament against its own collapse. So this is a morphological interpretation of different structure. And in fact, what is clear is that to be able to say whether the magnetic field is a critical element in the structure or is just a bystander, it is untrained by the structure formation, it's reacting to the structure formation, you need to understand
how much energy is there. And this is rather indirect with polarization study. And I'm just mentioning here that this is using, most of the papers are using this method called Davis-Chandrasekhar-Fermi, which, if you just look at the name, you know that this is a method that has been there for quite a while. And this is one of the expressions that you can have of this method. It can be complexified, and I will talk about this. But essentially, it assumes that the dispersion of the mean field, or compared to the mean field direction, is resulting from small-scale non-thermal motions. And you immediately see that to be able to derive an information on the strength of the field, you cannot do that only with polarization information. You need to have access to information on the velocity dispersion. You need to degrade your resolution because you want to have a dispersion, an estimate of the dispersion of the angle. So you can't work at the native resolution of your map. You have to integrate over some area. And you also need an estimate of the volume density. And on top of that, there are many caveats linked to the actual regime in which the assumption behind this equation. I've lost my sentence, but depending on whether the assumptions are valid or not in the region that you're looking at, and I will come back to that. But despite all these caveats, when you look at, for instance, in this paper, a compilation of comparison between data that are DCF measurements of the magnetic field and this dashed line, which is a sort of envelope of the Zeeman measurement of the magnetic field. So the Zeeman is this time, the Zeeman effect is this time giving you the strength of the magnetic field. You see that there's a consistency between these determination. There's lots of dispersion. Some of this dispersion is actually the uncertainty on the measurement, and they are not small because this is a decay. But still, it is making sense, and that you can also look at it on individual study. And this is a study on M17 by Hoang et al., where actually they compare the magnetic field to the turbulence, and they compare it also to the gravity to realize that, in fact, the magnetic field in this region is the dominant energy source. And they see this as an explanation to the observation that in the molecular cloud of M17, you do not find gravitationally bound clumps or high mass star formation. So, as I said, this assumption that polarization is giving us the magnetic field is really an assumption because there are lots of ifs inside. And if you look at it, here is a small list of elements that are in fact behind that assumption. Well, first, even if it was true that polarization was giving you direct access to the magnetic field, what you only observe is a plane of the sky component of a 3D field. And it's not even a simple projection because polarization doesn't add up as you would think any other quantity. You can cancel polarization by having on your line of sight components of the field that are in the reverse opposite direction. And so that means that you have in your map an unknown and biased spatial transform that is projecting from 3D to 2D. And then polarization can be detected because dust grains through these radiative torque alignment get aligned with the magnetic field direction. So just in that sentence, you know that the dust properties, its size distribution, its composition, the shape of the dust grain will leave a trace on polarization. And you also know that the alignment mechanism, and therefore the way the radiation field propagates into your medium, will also affect the capability of the medium to emit polarized light and you to detect it. And then you're sampling a line of sight. It's not a simple sheet of magnetic field. It's a field. It's a 3D distribution. And therefore, what happens on your line of sight and within your beam is going to affect the way you measure the quantity that you measure. And so the interesting structure of the observed medium is also impacting your capacity to measure a polarization signal and therefore infer a magnetic field.
And so if you view this, look at this, you can have two attitudes. Well, either it's okay, it's going to be intractable, and all hope is lost about anything. But you can also view it as opening new fields of interest with polarization studies, which ultimately will give you access to the magnetic field. And I think since we are in an interstellar medium field, all of these are interesting per se, despite the fact that they are, dragging you away from the ultimate goal of measuring the magnetic field. And so that's the last part of the one before last part of this presentation, where I've highlighted 3 areas where I think a lot of actions and progress will occur. First, I think there's a whole area of work on defining new tools and acquiring new data for morphological studies. As I said, all the morphological studies that we perform, they study 3D fields, but through a 2D projection. But the issue is that this 3D projection is not the same depending on the quantity we're looking at. Whether we're looking at the magnetic field or the column density or the velocity structure, the projection obeys different rules, and polarization doesn't add up, and it even cancels completely if the magnetic field is on the line of sight. It's there, but you don't see it. In density, if you're optically thin, if your tracer is optically thin, which is usually the case, it's relatively faithful, but if you observe a sheet on the side, it will look like a filament. So there's an ambiguity in the reality of the structure that you observe. And obviously, in velocity structure, if the velocity is perpendicular to the line of sight, then you have no information. And added to that, the identification of a velocity structure with a physical structure is not completely straightforward either, and often depends on a model or an assumption of what is actually the physical structure. So I think this means that we will need to develop or to enhance geometrically motivated tool that let us objectively assess the morphological properties of the field that we are observing. Obviously, increase the signal to noise on larger regions so that we do not only focus on the dense part, or what happens also when you are deprived of signal to noise, you focus on the part where the morphology behaves according to your expectation. Let's say in low signal to noise data, it's easy to do some data editing to have some observer bias. And I think also extremely important, there was a talk yesterday about this, which I could only read the slide because I was busy somewhere else. There's synergy with the simulations, because even if they don't introduce all the ingredients of the physics that we know is there, it is the only way that we can study how 3D properties survive the projection into 2D, and what kind of bias we have in this 2D data. So I really think that observing simulation is a very important step in understanding actually what these different maps are telling us. And just to illustrate briefly, well, this is, for instance, a way to enhance the data, the analysis that we do, which is to try and use some sort of tomographic observations approaches where we combine extinction and emission that sample different level of extinction. And in that study, what they showed is that depending on the column density that you were sampling, you can see changes in the relative orientation between the magnetic field and the structure. This is the transition observed in the Planck data between the low density region and the high density region, and they claim that at even higher density region, you can see again the change of orientation. And when I was talking about statistical, mathematical characterization, this was work done by Juan Diego Soler on the Planck data, where what he developed was this histogram of relative orientation. So on the whole map, you compute the relative orientation between the local field and the local density, and you trace the histogram. And all these graphs are tools to characterize the histogram, whether with respect to the significance of the existence of a peak or in this histogram, and the clustering of values around this peak. So all this is to try and take us away from, oh, I see alignment here, I see perpendicular perpendicularity here to put this into a more statistically significant context. There's one thing that I haven't talked about a lot, which is the polarization fraction. And in fact, there's lots of information in the polarization fraction, but it's information which is hard to interpret. When you look at the literature, you see that the polarization fraction is observed to follow trends with a number of quantities. There are correlation with the total intensity, there's correlation with the column density, there's correlation with the temperature. And these are informative and puzzling at the same time. They inform about the mechanism that are responsible for the grain alignments. They are complex to interpret because you have depolarization. So it's not just because you have magnetic field that you will have polarization. And so you can have high signal to noise, but still no polarization, despite the fact that you have a magnetic field. It will integrate effect from the grain property, the alignment mechanism, and the line of sight complexity. But the good thing is that we start with a relative consensus on the alignment and the alignment physics. So it's not all the time that we have a relatively solid interpretation basis to work from. It's the comparison to the observation that's going to be complicated. And so I think here the progress can be made by surveying environments where these radiative torques can be constrained, either because we know the geometry of the source or we have identified the heating source. We know the density structure from other elements. But one aspect which was mentioned yesterday by Mahmoud Tahani was to use the fact that we are building multi-band instruments. And so we have a spectral energy distribution of the polarization fraction. And in fact, this will allow us to get rid of some dependency because we are sampling the same medium, so it's subject to the same magnetic field, and the variation of the polarization fraction observed as a function of wavelength will therefore now be restricted to be, for instance, dust polarization, dust properties or alignment properties, and not magnetic field. But this can only work by combining the dust models, including polarization, to disambiguate the various mechanisms. And so it can get extremely complicated. This is an example of a paper which is currently in archive, which in fact they use it's on 30 radius, and they use the dust temperature as a proxy for the radiation field, and the column density as a proxy for the de-aligning collision. The fact that when the collision rate increases, the alignment effect is much less efficient. And they see in the correlation of the polarization fraction with either the column density or the temperature, they see trends that are compatible with the relative alignment torques, but also other trends such as the anti-correlation of the polarization fraction and the temperature here, or the correlation of the polarization fraction with the column density, which are less compatible with this, and that they interpret as signs of another effect due to radiative torques, which is radiative torques disruption, which is the sense that if you spin and spin the grains, you can reach a spinning velocity which is too strong for the grain cohesion force, and you will break up the grain. And so they build models in which they look at the dust distribution, and they look at they compute the minimum size of of grains that align, which impacts the polarization fraction, and see how this evolves as a function of temperature and density. They define a range at which, in fact, you reach this regime of destruction by spinning. And they show that depending on the trajectory you follow in this diagram, you can reproduce trends that you see in the data. So I think this is the kind of modelization that will allow us to understand better what the polarization fraction is telling us. And then obviously, I think this is probably the most difficult part, but I think it's a very important part. We need to put better constraint on the field strength, because this is how we are going to clearly demonstrate the importance of the magnetic field, or it's the fact that it's just there, but it's not participating. But this requires qualifying more methods. The uncertainties are currently relatively large and sometimes too large to be discriminant. An important aspect is that it really requires a multiple tracer approach. If you're just using polarization information, then we're missing a part of the component, and it's not independent on the intrinsic spatial resolution. We need high spatial resolution because, in fact, you will need to work at a lower resolution than your native resolution. And just to highlight a few of the questions, this is, again, one expression of this DCF method. And if you look at it, you see that, well, if you look at where it comes from, you will see that it assumes that there's equipartition between kinetic and magnetic turbulence. This is not always the case, and it's not easy to verify this a priori. There's a Q factor which is there to take into account elements which are within your beam and on your line of sight. The determination of the angular dispersion is not straightforward because it will depend also on the presence or the filtering of a large-scale order structure, the line of sight integration, the beam smoothing, or the interferometric filtering. So it's not absolutely evident how you are going to do this. And obviously, you need a correction to move from the plane of the sky field components to the total field component. So it's far from straightforward. And if you want to see the work that is currently done, you can start with these two papers, which try to calibrate this function against simulation, or develop or expand it or replace it with new estimates. I think this is a whole field of work on polarization, which will develop from simulation and from first principles to try and give us a better constraint on the strength of the magnetic field. And so to conclude, how are we going to do this? So I've talked a lot of projecting in 3D, in 2D or 3D things, so I do the same. I've made in this graph, so it's a volume, where I plot the wavelength range, the inverse of the map size. And so further away, smaller maps, and closer to us, larger maps, and the spatial resolution. So as of today, I mean, the instrument that has the highest spatial resolution, but also is focusing on the smallest region is ALMA. So I've listed 850 micron because that's typically the wavelengths at which we see results published today, but it can go in a larger range, and it's sitting there, I think, for a moment on its own. If you move a little bit further, well, you have a bunch of ground-based or airborne observatory, which are currently available and producing data. In fact, if you look at the polarization papers today, it's mostly Pole Plus and Pole 2. And we have one coming up, and we are waiting for results for this. This is the NICA 2 polarization version. Moving up in, so you get to be able to map larger area. These are facilities that should be coming up relatively soon. When BLAST, if you look at the website of BLAST TNG, it's supposed to be flying sometime. There's a project to equip the JCMT with a millimeter KID camera, and we are waiting for the decadal survey to see whether this survives the selection. And finally, the largest mapping capacity will be provided either, we saw yesterday, by CICAD Prime, which has an access to a very large scale structure, Lightbird, and the family of CMB experiments attached to it, as Ludovic was showing just a few minutes ago. And we are currently, we in Saclay are currently talking with the Russian team of Millimetron. So this will or will not happen today, to have a reincarnation of the instruments we were planning for Spica, which was here, and Millimetron is a 10 meter, so it's a higher resolution. And to really finish, I want to talk a little bit of detectors. So as Ludovic was saying, well, as you may have heard, first, I would say that if you look at the current instruments that are currently active and not heterodyne instruments, I think they're all using the same sort of approach to measurement of polarization, which is to have a bolometric detector of some kind, a KID detector, or based on heritage technology, on Herschel heritage technology, or transition edge sensor when they are available, and an optical device to modulate the polarization. So typically, this is a half-wave plate. This is working. The
the only issue is that the half-wave plate is becoming a critical element of the instrument. It is not easy to make a half-wave plate, which is a good half-wave plate for a large wavelength range. And furthermore, the half-wave plate will introduce quite a lot of instrumental polarization, which is not easy to calibrate out. So there are works, in fact, current development, which are focusing on producing detectors that are intrinsically polarization sensitive, and you do your modulation when you need to do it with another system, scanning, coming back to the same field and so forth. And this is what we had done for Bebop, where we had pixels that were carrying two sets of orthogonal dipole antennas connected to thermometers, and we were measuring the balance of power absorbed by the different polarized antenna, and to disambiguate between the 90-degree orientation, we were alternating pixels where the antenna were rotated by 45 degrees, and these detectors actually exist. This is a picture of them. So you have this 090 dipole pixel here, and plus 45, minus 45 there, and we are performance testing them in Saclay right now. And the JCMT M-Kit camera that I was putting in the diagram just the slide before will use this polarization sensitive KID array. And as Ludovic was mentioning, on Lightbird, there will also be polarization sensitive detector. Lightbird has decided to still modulate with a rotating half-wave plate. And this is, in fact, a critical element of the spacecraft. And so I thank you for your attention.
Thank you, Marc. We're going to take a few questions. I think Frédéric had questions.
Thanks. Actually, I wrote those questions while you were talking and we partially answered them, but I think that there are still a few points that we can specify. So the first question was about using multi-band polarization. You mentioned it, but I have the feeling that you talked about it to try to interpret the physical process at a given region. I was wondering if you could use multi-band polarized SUD to decompose the different layers of emission, so to recover the 3D structure of the sight line, because if you have different temperatures, you will have different intensities, so you can. Are there methods to do that?
Well, I haven't seen so far this being used, but I think it is true that if you're moving in wavelength, you are going to select, or you're going to change your selection function as which population of grain selected by temperature you're looking at. And so you could use that information and try to invert. In fact, what you do is you code that into your system. You say, okay, this polarization, the total polarization fraction is indeed a summation of different populations which are contributing with respect to their temperature, and you could try and do this sort of tomographic analysis. But what I think is that as you're introducing more dependency or more variables into your system, it means that the initial signal-to-noise ratio and the quantity of data you need to input into your system is increasing. So I think the first attempt will be to say, we assume that we have a consistent population, and we derive a global description of the properties of the dust. Then we come back to the whole question that was already there in total power. How is this global description of the dust actually related to the fact that what we observe is not a single dust population with a single composition and a single size distribution, but a composite. And but this, I think, will require, this is the second step of the analysis.
Yeah.
I also answer comment.
Yeah, very quickly then.
Okay. So just another comment. You talked about it, but so just polarization can be used to study dust physics, and there are a few things to test in the dust composition, and also the nature of the solumeter access depending on the scenario. TLS model or from the magnetic range, you have different production of polarization. So I just wanted to mention it.
I think Jérôme had a question.
Okay.
Okay. Like this.
Question on the relation between the way that we projected polarization and the systematics of the output plate. So there are two different things in your talk. You mixed, I think, a little bit. So you seem to say that if you project the polarization in the detector, you get rid of the systematics of the output plate. So I want to make it clear that this is not the case. So the systematics in the output plate will remain independently on the way that you project the polarization on the detectors or using an optical.
Yeah, but what I meant is that if you have polarization sensitive detectors, then you can remove the half-wave plate.
Okay, so if you don't use at all a half-wave plate,
yeah,
okay.
Yeah. No, if you have a half-wave plate, it comes with its own systematics, and it can be interesting to, well, that's what Lightbird does. It combines a half-wave plate, which is modulating the signal, the polarization signal.
Also Nika 2 and others, but in any case, even with the half-wave plate, you must have polarization sensitive detectors. So in any case, so the only question is, yes, you have to project the polarization at some point. So
okay, but for instance, in pilot, you have a half-wave plate, and the detectors are not polarization sensitive. They don't discriminate in a sense.
Maybe we can
okay,
have this
let's have this discussion.
There was a question by Cecilia, and then we'll move on.
Try to be fast, Cecilia. First, thank you. You clarified me a lot of these questions that I had on this polarization. And my question is a follow-up on what Federico was saying about the how can we reconstruct the structure and so on. Is it not possible to use this Gaia observation that reconstruct the via the extinction, the 3D of course, nearby ISM? Are there studies in this?
I think the issue is which range of column density will let you access. So I do think indeed that in diffuse region, and that will be quite interesting because so far we haven't looked a lot at diffuse region because they are fainter, and therefore the signal to noise that we can have on those is low, and we are more or less focused on the brighter region. But in the diffuse region, in fact, we can indeed combine with extinction to have an understanding of what's the structure. And I think this really the progress I think will come from injecting these constraints, and that's why I was saying that it will not be a straightforward analysis, because if we still stay at the level I compare a structure with another structure and it looks like it, or it's what I expect, or it's not what I expect, we will not make progress because there will be lots of different configuration, and it will only be by chance that the projection is such that we see what it's truthful to the actual combination. But statistically, I think this is what we need to study. When we have an information on the 3D structure coming, for instance, from extinction on a region, statistically, how can we use this to better understand what we are tracing in polarization? And I think, yes, this can be done, but it requires looking at simulation to understand how we build structure estimators mathematically and how we interpret them and how they relate to the 3D distribution.
Thank you very much.